All right, let's get into it. Every single day we're surrounded by these invisible threats. Some are ancient killers, some are brand new. But how do we actually find them? How do you unmask a culprit when the crime scene is an entire city and the weapon is totally microscopic? Well, today we're going to follow the clues with the original disease detectives.
Our story starts back in the 19th century. Picture a world that had absolutely no idea what germs were. Seriously. Most people believe diseases were spread by something called miasma, which is basically just bad air. But a new kind of investigator was about to change everything, using data as their magnifying glass to hunt for the real cause.
So the scene is the heart of London. And the mystery? A terrifying cholera outbreak. People were getting sick and dying within hours, and the city was in a total panic. The killer was swift, it was silent, and it was devastating. The big question wasn't just what it was, but how it was spreading. What was its mode of transmission? Okay, so this is our first huge piece of evidence, and it is brilliant. A physician named John Snow just wasn't buying the whole bad air theory. He suspected a totally different way of spreading. So what did he do? He started mapping. Each one of these dots isn't just a number, it's a person, a life that was lost. And as he plotted them, this chilling pattern started to emerge, all pointing to one single spot. What John Snow was doing, without even really knowing it, was pioneering a brand new field of science, epidemiology. You can think of this as the official toolkit for our disease detectives. It's not about treating just one patient. It's about investigating the health of an entire population to solve these huge mysteries and stop the killers in their tracks. So let's look at how they actually build a case. To accuse a suspect, whether it's a bacteria, a chemical, or even a behavior, you need a rock-solid case. A simple correlation isn't enough. You've got to prove causation. So, how on earth do epidemiologists do it?
And this is where the real nitty-gritty detective work starts. It is not enough to just see a connection. You have to prove it. Making the wrong call in public health can have absolutely devastating consequences, so every single step has to be backed up by solid, undeniable evidence.
And this is basically how they do it. Detectives use a checklist, kind of like this one. First, temporal relation. Does the exposure happen before the illness? It has to. Next, is the link plausible? Does it actually make biological sense? Is it consistent? Are other scientists finding the same thing? How strong is the link? And finally, is there a dose-response relationship, meaning, does more of the suspect lead to more of the disease?
This point on plausibility is so important. When John Snow claimed cholera was in the water, people thought he was crazy. They just couldn't imagine invisible microbes. This quote is a great reminder that what seems totally impossible today might just be a science we haven't discovered yet. So let's fast forward about a century and use this same checklist on a much more familiar villain. For decades, the link between smoking and lung cancer was hotly debated. But epidemiologists used these exact same principles to build the inescapable, rock-solid case that finally proved the connection.
And just look at this data. This is strength in action. The death rate for non-smokers with no asbestos exposure is 11. Okay, exposure to asbestos alone, that bumps it up to 58. Smoking alone, whoa, it jumps way up to 123. But when you combine them, the rate just skyrockets to 602. This is called interaction. It's like two culprits working together to become far deadlier than they are on their own.
And this idea of interaction of multiple factors, it has completely changed how we think about what causes disease. We've moved from hunting for a single suspect to investigating an entire network of accomplices.
Back in 1854, Snow's map showed that almost all the deaths were clustered around a single public water pump on Broad Street. This was his prime suspect. The mode of transmission wasn't bad air after all. It was a waterborne pathogen passed from person to person through this one central point.
In the early days, scientists like Robert Koch believed in a single-cause model, one germ, one disease. And that works great for something like anthrax. But now we know it's rarely that simple. For a disease like tuberculosis, the bacteria is a necessary cause, sure, but it's not sufficient. It needs accomplices, partners in crime, like poverty and malnutrition, to really take hold and do its damage.
So, identifying the cause and the mode of transmission is really only half the battle. The real goal is to use that knowledge to save lives. It's about breaking that chain of transmission and stopping the killer before it can strike again.
So what did John Snow do? He took his evidence to the local authorities. and he convinced them to take a simple but absolutely decisive action. They removed the handle from the Broad Street pump. By disabling the source, he broke the waterborne mode of transmission, and just like that, the outbreak ended. It's such a powerful symbol of public health in action.
Okay, so how do we use this knowledge to prevent future outbreaks? Well, the very first line of defense is what we call primordial prevention. Think of it as creating a world where the danger can't even get a foothold in the first place, like policies that make it harder for young people to ever even start smoking. Then you've got primary prevention. This is like giving people a shield to directly block a mode of transmission. Vaccinations are a perfect example, right? They protect our bodies from airborne or droplet-spread viruses before they can even attack.
But what if the threat is already there, just hidden? That's where secondary prevention comes in. This is like sending out a search party to find the danger early, through things like cancer screenings or checking for high blood pressure, long after any transmission might have happened.
And finally, if a disease is already struck, we have tertiary prevention. This is all about damage control. You know, helping someone regain strength after a stroke, for example, and managing the long-term effects of a disease to ensure they have the best possible quality of life.
So, from a single contaminated pump in London to our complex, interconnected world today, the work of the disease detective is more important than it has ever been. The mysteries have just gotten bigger and a whole lot more complex.
The field is global, and it operates at lightning speed. These epidemiologists are on the front lines everywhere, tracking diseases that can cross the entire planet in the time it takes to fly from one continent to another, often with completely new ways of spreading.
And their caseload today is just staggering. It includes the slow-motion epidemics of chronic diseases linked to our lifestyle and environment, the sudden explosion of emerging viruses where the first job is to figure out the mode of transmission, threats from environmental toxins creating new pathways to illness, and even ancient diseases like plague finding new opportunities to spread.
But here's the thing. No matter what the threat is, whether it's transmitted through the air, in our water, or through our own behaviors, the fundamental method is the same: the careful gathering of data, the mapping of patterns, and the rigorous application of the rules of causation. Jon Snow would recognize the work instantly.
And that's really the key takeaway. The detective work never ends. As our world continues to change, new threats will inevitably emerge. The question isn't if the next great health mystery will appear, but what it will be and how quickly our disease detectives can crack the case.